Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 2nd, 2025, so just 5 days ago. And this paper tackles why vision language models that fly on graphics processors fall apart on neural processing units at the edge. It introduces an NPU-Native architecture that keeps everything in integers while cutting end-to-end latency by up to 14 times, tripling decoding speed, and giving a context window 4 times longer on real automotive hardware. The paper is titled AutoNeural, Co-Designing Vision Language Models for NPU Inference. And as we will see later, the results point toward genuinely practical multimodal intelligence in cars and other edge devices. Alright, Figure 1 lays out how AutoNeural actually looks in practice, from inputs all the way through training. The left panel shows the NPU-Native architecture, where a mobile net vision encoder turns raw images into compact image tokens that flow via a simple connector into the language backbone alongside text tokens. The upper right panel illustrates the automotive dataset, which spans cockpit interfaces, different weather, varied interiors, and diverse demographics, so the model learns realistic driving scenarios. The lower right panel summarizes a 4-stage training strategy that moves from generic image-text association to highly domain-specific, quantization-aware tuning for the target chip. So while Figure 1 focused on the architecture and training flow, Figure 2 highlights what that design enables in the car. The overall figure shows 4 real cockpit scenarios where AutoNeural answers questions or generates actions in real time. The top panels illustrate in-cabin detection and out-cabin awareness, where the system explains child seat safety and parking rules because it can read both images and text. The bottom panels demonstrate reliable human-machine interface understanding in a visual plus conversational function call, where the model explains dashboard warnings and turns a spoken request into a structured navigation command. While Figure 2 showed real cockpit use cases, Table 1 compares AutoNeural against several strong vision language baselines on 5 benchmarks. The whole table reports accuracy percentages and parameter counts, so it shows that AutoNeural, with about 1.5 billion parameters, is compact yet competitive. The benchmark columns reveal that AutoNeural is near the top on most tasks, especially optical character recognition and hallucination robustness. The final average column highlights the key result, with AutoNeural matching or beating larger models in overall score. Alright, while Table 1 compared accuracy, Figure 3 shifts to latency on the Qualcomm 8295P neural processing unit. The full chart shows that the AutoNeural vision encoder is dramatically faster than the intern VIT baseline across image resolutions. At 256 by 256, AutoNeural takes about 28 milliseconds versus 163 milliseconds, which gives roughly a 6 times speedup. At 512 by 512, latency drops from about 1,400 milliseconds to about 100 milliseconds, a 14 times gain. At 768 by 768, AutoNeural still runs in about 280 milliseconds, while the intern VIT model does not fit in neural processing unit memory at all. Well, Figure 3 focused on vision encoder latency alone, and Table 2 expands that into an end-to-end comparison on the Qualcomm neural processing unit. The table shows that AutoNeural cuts vision encoder latency from about 1.4 seconds to about 100 milliseconds and supports larger 768 by 768 images. The central rows report signal quality, where higher SQNR and about 7 times lower RMS error indicate far more robust quantization. The bottom rows highlight language performance, with similar perplexity, roughly triple decoding throughput, and a 4 times longer context window of about 4,000 tokens. AutoNeural shows that when vision language models are co-designed with the neural processing unit in mind, integer-only inference can be both fast and accurate, with up to 14 times lower latency and robust quantization. The broader message is that future edge intelligence, especially in cars, will depend on hardware-aware model topologies. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.